Welcome back to the deep dive. Today we're tackling a question that seems pretty simple, but it can actually be one of the most misleading in statistics. What's the average?
Right. Because if you just take that average number at face value without, understanding what's behind it, you could be setting yourself up for a bad decision.
Exactly. So our mission today is really focused on you, the listener. Let's paint a picture. Say you're a recent grad, you've got two great job offers, company A, company B.
Pretty similar offers, right?
Yeah.
Benefits, culture, all that stuff lines up.
Yeah, really close. So you need a tiebreaker. You ask HR, hey, what's the average salary in the department I'd be joining?
Makes sense. A logical question.
And here's what they give you. Company A's mean salary, $49,220. Company B's mean salary, $41,400.
Okay.
So, that looks like a clear win for Company A, right? Like almost $8,000 more.
Yeah, on the surface, absolutely.
But okay, let's unpack this a bit. Why might relying just on that mean figure be, misleading? Why might Company B actually be a safer bet for your actual salary?
That's the perfect question to start with. Because that $8,000 difference, it can often be, a bit of a smokescreen. The average, what we statisticians call the mean, it's just one piece of the puzzle.
It gives you a number, but what does it hide?
Exactly. It ignores how spread out the salaries are.
Mm-hmm.
And critically, it ignores whether maybe one or two really, really high salaries are dragging that average up for everyone else.
Oh, okay.
So we need more tools. We
Yeah.
need to talk about, measures of central tendency, finding the middle, but also dispersion, how spread out things are, and even position where one specific value sits. That's how we really judge those job offers.
Right. So let's start with the mean because it's the one everyone kind of defaults to. You just add up all the salaries, divide by the number of people. Simple.
It is simple. And look, it's useful for benchmarks. We use it all the time. Like the average American commute time, one way in 2022 is 26 minutes. Now, obviously, that hides variation. New Yorkers take longer, about 33 minutes. Folks in Wyoming or the Dakotas, maybe only 18. But that 26 minutes tells us something useful nationally.
Or tracking changes, right? Like fuel economy.
Perfect example. A Honda Civic back in 2000 got around 27 mpg on average. By 2025, it's expected to be up to 36 mpg. The mean is great for showing those kinds of shifts when the data is, let's say, reasonably well-behaved.
Okay, well-behaved. But let's go back to our job offers. Company A, with that nice-looking 49K mean, this is where it gets really interesting. Why did it look so good?
It's the outlier problem. This is the mean's biggest weakness, really. You see 49K and you think, okay, that's probably around what people make.
Yeah, seems reasonable.
But what if we actually looked at the list of salaries in Company A? Maybe most people are making somewhere between, say, $18,000 and $23,000.
Whoa, okay. That's way lower.
Right. But then there's one executive in that same department pulling in, let's say, $300,000 to $35,755.
Wait, hold on. One person making over $300,000 just dragged the entire average up by that much. By $8,000 compared to Company B.
Precisely. That single value distorts the picture of what a typical employee earns there. The mean is great if you want the total payroll divided by people, but it's terrible at showing typicality if you have these extreme values.
So that's why we need something else.
That's exactly why we need the median.
Okay, and the median avoids this how. It's just the middle value, right? If you line everyone up by salary, lowest to highest.
Exactly. You just find the physical middle point in the ordered list. It doesn't care if the top salary is $50K or $5 million. The middle person is still the middle person.
Ah, okay.
We have a term for this. A statistic that isn't thrown off by extreme values, by outliers, we call it resistant. The median is resistant.
But the mean isn't.
The mean is definitely not resistant. So for things like salary data, where you often do have a few very high earners, the median usually gives you a much, much truer picture of what someone like you coming into the company might actually expect to earn.
Okay, that makes a lot of sense. But if the median is so much better for skewed data like salaries, why do we see the mean used so often by companies, news reports, everyone?
That's a really important question. Sometimes it's because the mean does account for every single dollar, and maybe the total picture matters for some analysis, but often, honestly, it can be about framing.
How so?
Well, if a company knows if salaries are skewed high, meaning a few big earners pull the average up, using the mean makes the company look better to potential hires. Sort of. Well, it could be a bit of mathematical spin.
Workplace psychology disguised as math. Got it.
pretty much.
And we should probably quickly mention the third measure, the mode.
Right, the mode. That's just the value that shows up most often.
So if more people earn exactly 20K than any other single salary, 20K is the mode.
Yep. You can have two modes bimodal or more, or sometimes no node if every value is unique. It's often less useful for continuous data like salary, but really good for categorical stuff like finding the most common car color sold.
Okay, so we've figured out how to find a more reliable center, especially with the median for skewed data. But just knowing the middle number, say the median salary, doesn't tell us if everyone else is clustered right around that number or if salaries are still all over the place.
Exactly. The center doesn't tell the whole story. We need to know how reliable that center is, how much variation there is. We need to talk about the spread or dispersion of the data.
Right. Where do we start with measuring spread?
Well, the simplest measure is the range, just the difference between the highest value and the lowest value, max minus min. Easy.
Okay, easy to calculate, but is it resistant?
What do you think? It depends only on the absolute highest and lowest values.
So no, definitely not resistant. If company A goes from 18K all the way up to that 335K outlier.
Right. That huge range tells you something. Definitely it tells you there's massive inequality, maybe instability. But the number itself is completely determined by just two people. Not very informative about the overall pattern.
Okay, so range is out for reliability. What's next?
So we move to the real workhorse of dispersion, standard deviation, often written as SD, or sometimes you'll see the Greek letter sigma or just as.
Standard deviation sounds statistical.
It is, and the calculation is a bit more involved. We don't need to get into the formula here, but the concept is crucial. It measures how much data values typically differ from the mean. Think of it as the average distance from the average.
Okay, the average distance from the average. How does that help us in practice?
It measures predictability. Let's use that amusement park example. It clarifies it really well. Say you're choosing between two roller coasters.
Okay.
Both have an average wait time posted, 35 minutes. Seems the same.
Right.
But then you find out ride A has a standard deviation of 6 minutes, while ride B has a standard deviation of 12 minutes.
Okay, so what does that difference in SD mean for my weight?
You want ride A, definitely.
Yeah.
That smaller SD of 6 means most wait times are packed tightly around that 35-minute average. You can be pretty confident your wait will be, say, somewhere between 29 and 41 minutes. It's reliable.
And ride B with the bigger SD.
An SD of 12 means the wait times are much more spread out, highly variable. You might wait 20 minutes, or you could be stuck there for 50 minutes. That high SD means more uncertainty, more risk of a really long wait.
Got it. So connecting back to the job offer, company A with that huge 335K outlier salary must have a massive standard deviation, right?
Absolutely, a huge SD.
So what does that huge SD tell me about how my salary might progress in that company?
It tells you it's unpredictable. It screams variability. While the mean is 49K, that huge SD confirms that most people, probably including you, are earning way less, and that 49K isn't a reliable expectation at all for the typical employee.
Whereas company B, even with a lower mean of 41K, if it had a much smaller standard deviation.
Exactly. A smaller SD suggests a much more stable, predictable salary structure for most employees. Maybe raises are more consistent, the pay bands are tighter. It feels less like a lottery.
Okay, predictability. That makes SD really powerful.
It really is. And it's especially useful when we're dealing with data that follows a nice, symmetrical, bell-shaped curve. That's where we can use something called the empirical rule.
The 68, 95, 99.7 rule.
That's the one. It's a fantastic guideline for bell-shaped distributions.
And it's great for things like standardized test scores, right? Like IQ scores. They generally follow a bell curve.
Perfectly. IQ scores are designed to have a mean of 100 and a standard deviation of 15.
Right.
And it's that symmetry, that bell shape where the mean and the median are basically the same, that lets the rule work.
So using the rule, what does it tell us?
It tells us that about 68% of people have IQ scores within one standard deviation of the mean. So between 100 minus 15, which is 85, and 100 plus 15, which is 115.
Okay, so roughly 2/3 of people are between 85 and 115.
Yep. Go at 2 standard deviations, so down to 70 and up to 130, and you capture about 95% of all IQ scores. Go at 3 standard deviations, and it's 99.7%, pretty much everyone. The SD becomes our yardstick against the mean.
All right, so we know how to find a reliable center, like the median, and we know how to measure the typical spread or predictability around the center using standard deviation. But what about just me, or one specific data point?
Right.
Like If I score 125 on that IQ test, or maybe I live in a state with a really high or low percentage of older residents compared to others, how unusual is my specific situation? We need something to measure position within the crowd.
Exactly. We've done center and spread. Now we need position.
Yeah.
And the absolute key tool for this is the z-score.
Z-score. Okay, what's that telling me?
A z-score tells you exactly how many standard deviations a particular data point is away from the mean of the whole set.
Okay, so it uses both the mean and the standard deviation we just talked about.
Precisely. It standardizes the value. If your z-score is positive, your data point is above the average. If it's negative, you're below the average. The size of the number tells you how far above or below in terms of standard deviation units.
Okay, let's use an example. You mentioned state demographics, like the percentage of people age 65 plus.
Yeah, let's say we looked at all 50 states. We could calculate the average percentage and the standard deviation for that percentage across all states.
Right.
Now, take a state like Florida. It's known for having an older population, maybe around 20.5% or 65 or older. If the U.S. average across states is, say, 16%.
Florida's definitely above average.
Right. So its z-score would be positive, and because it's quite a bit above 16%, it would likely be a fairly large positive number, maybe plus 1.5 or plus 2.0, depending on the standard deviation. That z-score instantly tells you Florida is significantly older demographically than the typical state.
And conversely, a state like Utah, they tend to have younger populations, maybe only 11% are 65 plus.
So Utah would be well below that 16% average. It would have a negative z-score and probably a fairly large negative number, like maybe 1 to some 1.8 or something.
So the z-score basically translates any raw number, salary, age percentage, test score into a universal measure of how weird is this compared to the average.
That's a great way to put it. How statistically unusual is this observation?
Okay. Z-scores seem powerful for individual comparison. What else helps with position?
Well, sometimes, especially with really large data sets like standardized test results for thousands of students, you just want a simpler ranking. That's where percentiles are useful.
Like if someone says Mark's ACT math score was at the 95th percentile?
Exactly. That tells you immediately that Mark scored the same as or higher than 95% of the other students who took that test. Only 5% scored higher. It's purely about relative rank.
Okay, simple ranking. Makes sense for big groups.
And closely related to percentiles are quartiles. Think of them as specific percentiles that divide the data up.
Quartiles, like quarters, 4 groups.
Precisely. They divide the ordered data into 4 equal parts, about 25% of the data in each part. You have the first quartile, Q1, which is the 25th percentile. The second quartile, Q2, which is the 50th percentile.
Wait, the 50th percentile, that's just the median.
It is. Q2 and the median are the same thing. And then Q3 is the third quartile, the 75th percentile.
Okay, Q1, Q2, the median, and Q3 chopping the data into 4 chunks.
Yep. And the distance between Q3 and Q1, that range covering the middle 50% of the data, has a special name, the interquartile range, or IQR.
Interquartile range, RQR. Why is that range useful?
Well, this brings us full circle, doesn't it? Remember how we said the mean and standard deviation aren't great for skewed data or data with outliers?
Yeah, like our company A salary example. Use the median instead of the mean.
Exactly. And for the spread. Instead of the standard deviation or the range, the IQR is the resistant measure of spread that pairs perfectly with the median.
So for skewed data, you use median and IQR together instead of mean and standard deviation.
That's the best practice, absolutely. If you suspect outliers or skewness, like in salaries or housing prices, often the median tells you the typical center and the IQR tells you the spread of the middle half of the data, ignoring those extreme ends. They give a much more stable and trustworthy description.
So if company A, the one with the 335K outlier, had published its median salary and its IQR,
that combination would give you a much clearer, more honest picture of the typical salary range and stability within that department than the mean and standard deviation ever could. Much more useful for your job decision. #outro.
Wow. Okay, so let's wrap this up. What does this all mean for us? We started with what looked like a simple choice between 2 job offers based on average salary.
Right, a seemingly simple number.
And we ended up realizing we need a whole toolkit just to understand if we can even trust that average. We now know just looking at the mean, especially without asking about outliers or spread, is basically, well, it's statistically careless.
It really is. Synthesis is key here, Think of it like this. The mean or median tells you where the center tends to be. The standard deviation, or the IQR, tells you how predictably the data clusters around that center, basically, your risk or uncertainty.
Okay, center and predictability.
And then the Z-score tells you how unusual or extreme a single specific observation is compared to that center and spread. Understanding all three gives you real insight. It's not just having the knowledge, it's applying it critically.